Swayam Prabha. Digital India. Educated India.
Now let us try to eliminate the disadvantages associated with galvanometer and try to make it a perfect system. So the disadvantage like the loss of energy on the mirror, it can be eliminated by appropriately polishing the mirrors in such a way that the absorption can be minimal and reflectivity can be the maximum when the laser beam strike on the mirrors. It can be done by appropriately coat the layers with a highly reflective material, or you can polish the surface of the mirrors appropriately. The other two are the defocused laser beam on the platform and laser beam spot distortion. So let us try to consider these both cases, and this type of correction in the beam is called as beam correction. So for example, if this is the laser beam getting deflected from the galvanometer, this is the position when it is not deflected, it just vertically passed on the platform. This is the build platform and this is the laser beam. So if the laser beam is getting deflected and falling vertically on the build platform, then this is the laser beam, and you can see its focal point will be at this location. So let me call it as focal point. Now if the laser beam is getting deflected by the galvanometer and this is the new position of the laser beam, in that case, as the focal distance remains same, this will be the focal point, and hence in other words, the locus of the focal point for deflecting beam at different angle will follow this spherical path. In 2D plane, it will be a circular path, of course. So this is what happened when the beam passes from a spherical lens. So typically the scenario is like this. This is the laser beam coming from the top. It is getting deflected by striking on a galvanometer, and after getting deflected from the galvanometer, it passes through a spherical lens. Why it is passing through the spherical lens? Because further we want to focus this laser beam at a particular location. We have just seen if the laser beam which is getting deflected by the galvanometer and passes through the spherical lens to get focused, the locus of the focal point lies on the on a circular path. So that is what you are seeing here also in this image again. So this is the focal point. Now if the laser beam will pass through another point, so for example the position of mirror is not like this, it is something like this, and maybe the laser beam is getting deflected and going here, then again it will get focused at this point only. It will not focus on the target plate, which is your build platform. Therefore what you will get on the target plate will be having some different diameter, because you know that typically when a laser get focused, so for example this is a typical laser, this is the collimated beam, when it passes through a lens, it get focused at a particular point and the laser beam typically travel like this. So this is the minimal west radius and also called as focal point. The distance from here to here is called as focal point. Now what we want to keep this minimum diameter at a particular location on our build platform, while like I already mentioned, its position will follow a circular path, means the focal point will be always on a circular trajectory. So for that we need to use some special kind of lenses, and hence the process is called as beam correction. The solution for this is by using some lenses called as flat field lens. These flat field lens the working principle of the flat field lens is shown on this slide. So what happened? Now this is not a conventional spherical lens, it is a flat field lens. Please note that when the laser beam strikes on the galvanometer and it gets deflected, it passes through the flat field lens, and hence the focal point is always lying on the target plate, that is flat. Earlier you have seen the focal point was observed always in a circular path or a circular screen. But if you use flat field lens, the focal point will be achieved on the flat plate. Now this is very useful, and hence now all the time the focal point will be achieved here. Also, if the laser beam is striking the flat field lens at an angle theta, then I can say this height h will be equals to focal distance f into tan of theta. Where tan theta? Tan theta is nothing but the tangent of the angle theta made by horizontal axis and the laser beam striking on the lens. Now, in other words, I can write it like this. So, we can write h equals to f into tan theta. Now, let me differentiate this particular term. If I differentiate this term, I will get dh by dt equals to f and the differentiation of tan theta, that is sec square theta into d theta by dt. Now again I can write this term dh by dt, which is nothing but the change in this distance. This distance means where the focal point is observed. Hence it will be the velocity of this point, means it is moving up and down. So for example, my galvanometer is moving with some angular velocity omega h, then the point h or this particular point here will move up and down. So the rate of change of this distance h will be given as vh, the velocity of point, this particular point, and hence it will be equals to the constant value f sec square theta omega h. Here I can further simplify it and write it like this. It says that vh equals to f omega h by cos square theta. So we can note that the velocity vh, what is vh? Vh is the velocity of the point of this laser beam point. So the velocity vh of the laser beam on the flat surface is a function of angular velocity of the galvanometer and the angle of incidence theta. Therefore, to keep the constant velocity, for example, you want to keep this value constant because this is desirable, right? When you are curing some wet photopolymer material here, you want to move with a constant speed throughout, right? So, to keep this value constant, Vh constant, you have to keep varying the omega h also, as theta is always varying. Therefore, the electronics of such system become bit tedious and it is difficult to control such systems. However, it solve our purpose. This particular lens, flat field lens, solve our purpose. They are giving us the focal point here, but as the image which is created at a height h follows the f into tan theta rule, it is giving some issue when the laser beam moves on the flat surface. In that case, the velocity is not a linear function, or velocity is not only proportional to the omega h of the mirror. It also depends on the angle of incidence theta. Let us discuss this problem through an example. This problem says a single axis galvanometer, means only one mirror is there, with a range of plus minus 15 degree is used in a SLA process. The beam deflected from the galvanometer is passes through a flat field lens. To keep the focal point at a distance of 500 mm from the flat top surface of the liquid wet, in order to obtain the constant velocity of the laser spot at 10 meter per second, determine the range of the galvanometer's angular velocity. So, what is given to us? It is given that the velocity Vh should be constant and it should be 10 meter per second. It is also given that the focal point is at a distance of 500 mm, means the focal distance f is equals to 0.5 meter. Now if I want to find out what will be the omega h when theta varies from plus 15 degree to minus 15 degree. Now my objective is to find out omega h when theta varies from plus 15 degree to minus 15 degree. Hence, let me put all these values in this equation and I will get omega h equals to 20 cos square theta. Now, if this is omega h, when the maximum value will be achieved, maximum value of this function will be achieved when theta is 0. Because at theta is 0, cos theta will be maximum. Hence, omega will be 20. And the unit will be rotation per second. Now, if theta is 15 degree, because the range of theta is greater than minus 15 and less than 15. So, either I put minus 15 or plus 15, cos theta will give me the same value. Therefore, I am putting just 15 and hence I will achieve the minimum value of this function. So, the minimum value of this function will be achieved at theta equals to 15 degree and hence the omega minimum will be 18.66. Therefore, I can say that to keep the velocity Vh constant to 10 meter per second and the laser beam is getting deflected by a galvanometer from minus 15 degree to 15 degree, in that range when the beam is traveling, for example, from center to this particular point where the galvanometer is changing from 0 to 15 degree, the angular velocity of the galvanometer should vary. It should be maximum at the center, 20 rotation per second, and in the end it should be 18.66 rotation per second. And in between also one can calculate it by this formula. So the task has become a bit difficult now. I cannot achieve a constant velocity if I use the constant omega h in this case. So what is the solution? So the solution is I need such a lens which can give me the focal point at f into theta instead of f into tan theta, and such lenses are called as f theta lens. So to overcome the issues associated with flat field lens, the f theta are used along with galvanometers. The spot position for f theta is roughly the product of f into theta as you are seeing here. It is unlikely which we use in flat field lens. In flat field lens, what was it? It was f into tan theta. Now let me see the rate of change of this distance h. So if I am writing h equals to f into theta, the rate of change of h will be equals to f into d theta by dt, and d theta by dt is nothing but the change in the angular position of the galvanometer, and hence it is nothing but the angular velocity of the galvanometer, or in other words I can write it as omega h. So Vh is equals to f omega h. Here you can see this particular equation is independent of theta. There is no theta term here. Means whatever the angular velocity will be, it is directly proportional to the velocity of the beam which is moving on the flat surface. Now if I move on the flat surface from maybe this point to this point, the angular velocity of the galvanometer will remain same to achieve a particular velocity at the bottom. Keeping the constant velocity at the bottom will give us lot of benefits, because if the velocity is constant, the energy exposed or the top layer exposed to the energy will also remain constant, and hence you need not to worry much about changing the angular velocity of the galvanometers based on the position of the laser beam spot on the flat surface. So f theta lens is a solution for achieving the focal point at the flat field here. So this slide summarizes and shows the commercially available f theta lenses. So if the light is passing through a spherical lens to get focused, the focal point will be achieved on this circular trajectory, which is not desirable because we use a flat bed, because liquid is spread on this flat bed only. So assume that the whole thing is rotated by 90 degree. Now if we have also seen, if we use flat field scanning lens, what happened? The focal point is achieved at the flat surface, but the distance or the focal distance from the center axis is a function of tan theta. Means f into tan theta is the distance at which the focal point is achieved from the center. we have seen the issue in such cases is that the velocity of the laser beam spot depends on the angle of incidence theta. Then we have also discussed the f theta lens, where the focal point is a function of f into theta, and hence the velocity of the laser beam spot is just directly proportional to the angular velocity of the galvanometer. Hence this type of lenses are usually preferred in 3D printing as well. So any additive manufacturing system which uses galvanometer uses normally f theta lens. But using f theta lens only is not solving our all the issues associated with the galvanometers. Other types of issue are further discussed here. So if the galvanometer is deflecting a laser beam which is further getting focused by utilizing the f theta lens at a flat field, you will find that the laser beam is striking vertically. So means this axis angle is 90 degree from the build plate. In that case, if I look at the laser beam's cross section, if this is the zoom view of the same, you will find that the laser beam spot diameter is d, which is the focal diameter also. But now if let me consider the case when laser beam is striking at an angle. By utilizing the f theta lens, you are definitely getting the focal point at this particular surface only. But if I zoom in here, you will see it like this. The laser beam is striking at an angle. Now, although the focal point is here, but it is not in this plane. It is of course here, but the actual plane will be this. Then in that case, distance from here to here, this distance is d. But as the laser is incidenting at an angle theta, this angle will be theta, and hence if this angle is theta, this angle will be 90 minus theta, and if this angle is 90, this will be again theta. So let me write this angle as theta. So if this angle is theta, so I can easily find out the length of this particular projection, which is from here to here. This length will be d upon cos theta if I use this particular triangle. So just look at this particular triangle, and hence this particular length will be d by cos theta. In other words, it will be d into sec theta. So the projection of the laser beam, which is although having the focal point here on a flat surface, will be an ellipse now. It will no longer look like a circle when the laser beam is falling vertically. And the major axis of this projected beam spot will be d into sec theta, which is nothing but this distance from here to here, which is d by cos theta, or in other words d sec theta, and the minor axis will be same, that is d. Hence in that case, the area of this laser beam spot will be a equals to, we know that, pi into major axis into minor axis, so a into b. So what is major axis? Major axis is d by cos theta, and the minor axis is d. Hence you will get pi by 4 d square divided by cos theta. And hence what is this pi by 4 d square? This is the area of this spot when the laser beam is incidenting vertically. So I am calling it as a naught, and it is nothing but pi by 4 d square. Now if I use this and I write a naught here divided by cos theta. So the area of the laser beam which is projected at an angle theta will now get increased by this. So the new area will be a naught by cos theta. As cos theta is always less than 1, of course we know that this particular value will be always greater than a naught. So basically what happened? When the laser beam area which is projected on the flat surface is getting increased, the intensity will be decreased. We know that, we just discussed in last lecture, that the intensity of a laser beam I is given as the laser power PL divided by area. And if the area is increasing and laser power is constant, the intensity will reduce. In other words, it is also called as power density. The power density will reduce, and hence the energy available per unit area with the wet photopolymer falling inside the laser beam spot will reduce. And in that case, to overcome this issue, you have to increase the laser power appropriately when the laser beam is striking at an angle theta. So in other words, the power of the laser is now becoming a function of theta, and it is very difficult to control. So what we need to do, we need to find a method where I can strike my laser beam always perpendicular to the flat surface of the wet photopolymer. So let me just show you, before giving the solution, an example here. In a wet photopolymerization based process, a laser beam got deflected by an angle of theta after striking the galvanometer. So this is the galvanometer, and the laser beam is striking here, and it is getting deflected by an angle theta from the vertical. If the power of laser is PL, if the laser power is PL here, what will be the power intensity in the laser beam spot? So we know that in that case, the spot area A will be equals to A naught, which is the area of the beam when the laser is striking at an angle 0, means vertically, divided by cos theta. Theta is the incident angle made between the laser beam and the vertical axis. If I use, now this is the new area, hence the intensity will be equals to laser power divided by the area of the laser. Hence the intensity will be equals to PL by A naught cos theta. What is PL by A naught? It is the intensity of the laser at this location when the laser beam strikes vertically. So in other words, I can write I equals to I naught cos theta. So the intensity has reduced by cos theta. As theta is always less than 1, of course this quantity will be always less than I naught. So the change in intensity is one issue. Another is the change in the energy absorption also, because we know that as per the Beer-Lambert's cosine law, the energy absorbed by a surface is directly proportional to the cosine of the angle between the striking beam and the normal of the surface. So if the laser beam is striking vertically, then the absorption will be maximum, and if it is striking at an angle, the energy absorbed by the surface will reduce by the product of cos theta. Let me just show it to you here. So if in this case, now I am considering this case, the laser beam is striking at an angle theta from the normal of the surface. This is the normal of the surface, 90 degree. Then the energy absorbed by the surface will be equals to the maximum energy absorbed, which is the case when laser is striking vertically, and means at 90 degree, which is also along the normal of this surface, because this is a flat surface, hence normal will be also vertical. So energy absorbed in this case will be equals to energy absorbed in this case multiplied by cos theta. Hence you can see the absorbed energy also itself has reduced, and more energy will get deflected now from the surface. So these two major disadvantages has to be resolved now. So the solution for that is utilizing a telecentric lens. So this was the f theta lens, right? We have seen this f theta lens. In the f theta lens, we have seen that when the laser beam strikes at an angle theta from the horizontal axis, this angle is theta in this case, it strikes at an angle theta, which is the angle between the surface normal and the laser beam striking. Then the focal point will be always on this flat plate, and also the distance of the focal point will be equals to f into theta on the flat plate. This distance is f, this is the focal distance. Now if this distance is f and h is equals to f into theta, the issue is resolved. The focal point is on the flat plate, but the laser beam is striking at an angle. This is not acceptable, because we have seen two major issues. One, the shape of the laser beam striking on the flat plate changes. It changes from circular to ellipse, and also we have seen, due to the incidence of the beam at an angle, the absorption of the energy reduces by cos theta. Therefore the solution for that is if we use telecentric f theta lens. So this telecentric lens, basically what they do, they project whatever beam falling on it perpendicular to the flat surface. So now the laser beam is falling onto the this telecentric f theta lens, because of f theta property, the focal point will be always here on this screen, and also the laser beam will be projected always normal to the screen. Hence the issue is resolved. If the laser beam is perpendicularly falling on the screen, always the energy will be absorbed maximum, and also due to the perpendicular falling of the beam spot will remain always circular, and hence there is no change in the power density. So basically telecentric lens facilitates normal incidence of the laser onto the target plate. However, a major disadvantage of telecentric lens is that the scannable area is limited by the size of the lens, because the entire area, for example, the galvanometer is deflecting by 15 degree, right, or maybe plus minus 25 degree, then the size of the lens should be within that area, okay, so that all the beams are falling should pass through the telecentric beam, then only it will project them vertically. Due to this limitations in the size of the lenses, you please note now here that all the additive manufacturing systems, those are using galvanometer, are limited in size. That is why when you see all these machines like SLM, SLA, they have the limited size. For example, the SLM machines, typically when they use a single galvanometer, the size of the bed is limited to 250 by 250 mm or 300 by 300 mm. If you want to use beyond that, multiple lasers are used. The single laser with single galvanometer is not usually can give you the working area more than 300 mm by 300 mm. And the reason behind that is this telecentric f theta lens. Now I'll give you another very quick solution for this problem, but not really very exact like we achieved by the f theta lens or utilizing the telecentric lens, but a very approximate solution to achieve the almost perpendicular incidence of the beam on the flat surface, and also which will give you an approximate solution of falling the beam onto the bed perpendicular to the flat surface approximately. So we know that, for example, this is your bed, and maybe at the center the galvanometer is mounted at a distance of h. So if I look at the this is the top view, and if I look at the side view, it will look something like this. This is the build plate, and this is my galvanometer. Here beam is striking and then falling down like this. So if it is striking at an angle, of course the beam will deflect somewhere else like this, and if you strike here again, it will deflect somewhere else. So basically we know that the focal point is lying in a circle, right? So the focal point is here. If I don't want to use f theta lens, what is the solution? So I can use a very large height. So if I use, for example, very large height, and I am projecting my laser from a very large distance, in that case the radius of this circle will also increase. And let me just redraw approximately. This is your flat surface, and it's a very big circle, and your laser beam is very far away from the flat surface. Then what you will achieve within this range, within the range of maybe plus minus 10 degree of the galvanometer or plus minus 15 degree of the galvanometer, you will get almost flat area, right? The focal point will be almost in flat area. So theoretically, if this is at infinity, you will get a flat surface, absolute flat surface here. So approximately, if you use a very large height, you can really achieve approximate perpendicular incident of the beam, and the focal point will also lie approximately on this flat surface. That is the another reason why 3D printers are very tall. And if you utilize this concept of increasing the height with the galvanometer, of course the size of your telecentric lens will also reduce, and hence you can increase the build area also. But this height really increases drastically to achieve this type of approximate incident on the flat surface, to achieve perpendicular incident of the laser beam and uniform intensity without changing the shape of the laser beam. So typically, now let me just summarize the whole thing for the beam correction. The galvanometer is used. I have also given you a demonstration on the prototype where I have shown you the laser beam is striking on the galvanometer and then falling down and how it moves. We are also capable now to convert the XY coordinate of the contour or the point which we want to locate into the theta x and theta y. Those are the angular position of the two mirrors of the galvanometer. So the laser beam comes, falls onto the first mirror and then falls onto the second mirror and then falls down. There is a lens used in between, which is the telecentric f theta lens, which corrects the beam shape and also make sure that the focal point is on this flat screen. If this lens is used, always the laser beam will fall perpendicular to the surface, and all the time you will get the perfect shape of the laser beam spot at each location, and hence the property of the part you are building will remain very constant. So this is how we correct the laser beam shape in a typical SLA based process. Now we shall discuss about the recoating system in the SLA. So far we have already discussed about the laser beam, basically the fundamentals of laser beam. Also we have seen the laser curing, and now we just discussed the third subsystem, that is the galvanometer, along with the other optical systems. Now let us move to the fourth subsystem of the SLA machine, that is a recoating system. So the recoating system basically consisted of three main steps. As you are seeing here, this is the complete process of SLA, in which we start from this step where the laser falls onto the part and it cures the liquid wherever it falls. Then after that, after curing a complete layer, the entire bed goes down, and it goes down by a value higher than the layer thickness, and this process is called as deep dipping. Then after that, the part elevates and it goes slightly above the layer thickness, and a wiping blade, or also called as doctor blade, wipes and remove the excess material from the layer. Then after that, the build part takes its original position and the new layer is now available for curing. So before that, of course, a leveling operation is performed, which used to check whether the liquid layer is available at a certain level of height or not, because sometimes the part which is here got shrinked, and due to that there will be less liquid material available here. Hence in that case, more liquid is further processed, and if it is not, then definitely it will go for the curing and the cycle will repeat itself. So in this, from here, step 1, 2 and 3, they all are coming under the recoating. In SLA process, the recoating takes around 5 to 10 times more time as compared to the curing time, because this recoating cycle is so complicated that it takes lot of time. So what is recoating? Recoating is the process of establishing a new layer of fresh resin over the previously built layer. A successful recoating system is one that is capable of establishing a fresh layer of liquid resin of thickness exactly equal to the desired thickness, that may be, let us assume it has to be TL, within a reasonably short period of time. Please note that an incorrect spread of the layer thickness will adversely affect the accuracy of the product, and as a result you may not get the very fine object. Due to the finite value of the viscosity and surface tension of the liquid resin, it is very difficult to meet these requirements from a recoating system. As a result, one need to adopt very complicated recoating cycle which involves the following stages. First is leveling, second is deep dipping, third is elevating, fourth is sweeping, fifth is obtaining the build position, and sixth is Z weight. Let us discuss about these 6 steps of recoating in detail. So the first step is the leveling. If resin did not shrink upon polymerization, which is usually happened because after polymerization the density of the part got increased, this step would have not been required at the start. However, it is required to ensure that the resin was at proper Z level. So, this is the liquid, and for example, this is the height I am measuring from here. So, if it is not at a particular Z level, what may happen? It may go slightly down, and it usually happens because of the shrinkage into the part. Typically, a resin goes up to about 5% to 7% total volumetric shrinkage upon curing. A level compensation system, contact or non-contact, is implemented in SLA. So, for example, this is a non-contact system. There is a laser which is coming here. So, this is the emitter and this is the receiver, and the laser got reflect from here, and the height can be measured. If this height measured is increasing, that means more material is required to be filled here, as due to shrinkage some material has lost. Therefore, the level compensation system maintain a tolerance in the Z level, only in the Z level, only in the build direction basically. If the resin lies within this tolerance limit, the leveling operation is completed. So, the job of this operation is only to ensure whether the liquid resin is available up to a certain level or not. If not, it will give a signal to a system which will supply additional material to the tank. So, next operation is deep dipping. So, for example, this is your build platform. This is your liquid resin. Here you are seeing liquid resin. And this is the cured part basically. So, already cured. So, what happened? The elevator, which is, this is the elevator, fully immerse the previously completed part under the computer control to allow the resin to flow over the part. So, it is going down in such a way that the resin from the bottom side will flow over it and completely cover the already cured part. So, this is the cured part. Owing to the high viscosity of the resin will take quite some time before it assume a level surface over the entire part because of the finite value of the surface tension. And of course, if the surface tension is less, it will take less time. If the surface tension is high, it will take more time to get settled over the cured part. Hence, what will happen when we dip the part into the liquid vat, a depression occur. This particular valley, what you are seeing here, this depression, it occurs in the resin surface just above the part. The depression can be quite significant over the region with trap resin volume. Such volume occur when there are pockets of liquid resin within the part interior that do not have connecting passes to the rest of the liquid of the wet. So, for example, I am making this cylindrical object which is close at the end and having a finite thickness. So, if I am building this part, and in this portion always liquid resin will be there because this is not the part of the final object, the center region. Hence, always liquid material will be here. This is called as the trapped resin volume. So, in these regions, what happened when the material flows over the part in the deep dipping operation, the depression is more just above this trapped volume region, and it takes more time to get settled here. As this trapped volume is not connected with anything, hence always some liquid material will be there. So, basically the time taken, which I am representing by TD here, time taken for deep dipping. Now, this time taken TD, which is represented here for the depression to be closed, is thus given by this particular formula. So, the time taken to cover this whole thing is directly proportional to the critical radius into viscosity divided by the HD square, where HD is the depth of the depression. Basically, how deep you are going, then the depression depth will be more. So, that is the height of that. So, RC, let us discuss about RC first. It is called as critical radius or critical circle radius for that particular cross section. I will discuss about this in detail. Mu is the viscosity of the resin and Hd is the depth of the depression, like I already mentioned. Of course, if mu is high, mu means the viscosity of the liquid resin is high, it will take more time to close the depression created here. Now let us discuss about RC. So a critical circle is the maximum distance on any cross sections geometry that resin must travel to flow of the part. So for example, this is the cross section we are obtaining for a particular level of Z height. So this is the cross section which I am highlighting here in the red color. In this, a circle of radius R1 can be drawn, and this R1 is the maximum possible radius for the circle which can drawn inside this cross section. Now I mean this R1 will be called as RC. Now let me consider another cross section. Here this is the cross section, the triangular one. The maximum radius circle which can be drawn inside this cross section is shown here. Here this R2 is of course the critical radius. And in similar fashion, in this particular cross section, this is the maximum radius I can make, and this is my cross section here. This R3 will be nothing but the RC, critical radius. Now if you look at the object 1, object 2 and object 3, it is obvious from the diagram that R1 is greater than R2 is greater than R3. Therefore, if the viscosity and deep dipping height is same, then this particular cross section will take more time to cover the entire region by the resin during the deep dipping operation as compared to the other two objects here. Let us now look at a video which you can also do an experiment at home. We have two objects of same surface area but different critical radius. We have a vat of liquid photopolymer where we will do the experiment to test how much time it will take to sink the objects. So this first object, which is obviously having a lower critical radius, can sink into the wet photopolymer within approximately 10 seconds. The another object, which is relatively having a larger value of the critical radius but same surface area as we see in the last object, but you can see it is taking a lot of time. Here the approximate time to sink this object into the wet photopolymer is about 23 seconds. Hence with this experiment we can conclude that the recoating cycle, which is critically depend on the deep dipping, highly depends on the critical radius of the object, not on the surface area. So this is the critical radius. Assume now if RC and mu both are constant, then the only possibility of reducing time taken for filling the depression is by increasing the dipping height, that is HD. And also you can just observe this formula. You can see the time taken for closing the depression is proportional to the 1 upon HD square. So if the height HD will increase, the deep dipping height will increase, its square will be responsible for decreasing the time for closing the depression. And that is why it is called as deep dipping, because we just increase this height. Because we do not have much control on mu. Mu of the resin is constant. And also this RC which we are obtaining is depending on the CAD model. And the cross sections also we cannot change. So the only process parameter which we have in our hand is HD. And this is, if we increase it, then definitely we can reduce the time TD drastically. As this HD is usually high, the process is called as deep dipping. Now let me consider an example. In a machine SLA 250 and SLA 500, the deep dipping is about 7.5 mm and 18 mm respectively. Then let us try to observe how fast this machine SLA 500 will be as compared to SLA 250, particularly for the deep dipping operation. So we have already seen the time taken for closing the depression is directly proportional to 1 upon HD square. Now let me consider the time required TD for closing the depression in a 250 SLA 250 machine. It will be proportional to 1 upon 7.5 square. In a similar fashion, the time required to close the depression in 500 SLA 500 will be directly proportional to 1 upon 18 square. Now let me find out the ratio of these two, means TD 250 divided by TD 500, and this will be equals to 18 square divided by 7.5 square, and this ratio is coming to be around 5.76. So you can see that the time required to fill the depression in SLA 250 will be equals to 5.76 times more than the time required to close the depression in SLA 500. Means, so as you can see, just by increasing the deep dipping height by 10.5 mm only, the amount of time required to close the depression has decreased by 5 times. And you can observe how fast the machine can be just by increasing the dipping height. That is why this process is called as deep dipping, because going deeper is the beneficial for us. So why do we not really have all the time very high value of this deep dipping? This is because the amount of the deep dipping will remain surplus, or the amount of the resin available in the deep dipping height will not be useful in the end, and that has to be always there in the tank. Let me just show you. So for example, we are building this part and it is in this tank, and I have already built the part up to this height. Now it has to go down up to a certain limit of height, hence that height is nothing but your HD, and if HD material is available here, this is the height HD. So all the time this much material should be available just for deep dipping, and hence it cannot be really useful, because the last layer if I am building cannot be, because if this is the height of the object H, then the stroke will be H plus HD, the stroke of the elevator, and hence this HD is always a clearance. Also excess material will be always there, that is equals to the height HD. This is basically a lost on the inventory side, and that is why we have a limitation. Now let me consider another example where it is asked to find out the ratio of the depression closing time required for the two cross sections showing here in the figure. So this is figure 1 and this is figure 2. So as we have already seen, the time for closing the depression in the SLA process is directly proportional to the critical radius of the cross section. What is critical radius? We have already discussed that it is the maximum radius circle which can be drawn inside the cross section. Now in this case, of course, it's a circle, and the maximum circle I can draw will be nothing but of equal diameter. Hence RC for this figure 1 will be equals to D by 2. In a similar fashion, now here if you observe, there is no material here, right, and there is material available here. Hence I can draw a circle, and this will be the circle of maximum possible radius. You can see that anywhere, and its value will be the distance from here to here, it is D. That means the distance from here to here, it will be half of 0.5 D, that is 0.25 D. This is the distance from here to here. Hence RC for 2 will be equals to 0.25 D divided by 2. Now let us find out the time to close the depression for case 1 will be proportional to D by 2, and the time for closing the depression for case 2 will be proportional to 0.25 D by 2. Now let me take the ratio of these two, equation 1 and equation 2, and you will find T1 by TD2 is equals to 1 upon 0.25, and which is of course equals to 4. Hence, the time required for closing the depression in case 1 will be 4 times more as compared to the time required for closing the depression in case 2. This is based on the analysis of the critical radius. Assuming that, of course, mu and HD are same for both the cases. As during the slicing operation, you already have the data corresponding to the cross sections, we can predict in the beginning itself, during the pre-processing itself, the amount of time will be required for closing the depression on each and every cross section, and hence that particular time will be given to that particular layer. So this is basically a pre-processing step which can be taken care later on while building the part. Now let us discuss another step that is called as elevating. So the third stage starts once the depression has closed. So already we have seen the time required for depression to be closed. The platform then elevated until the top layer of the part is above the resin surface. So you can see ideally the part should reach up to a certain value here, but it is going slightly above. It is because when a wiper or doctor blade will wipe this excess material from here, it should not disturb the previous layer. If it will disturb the previous layer, you will generate basically some waviness here, and you have to wait a lot of time to get these waves settled. Therefore, usually it gets elevated slightly above the layer thickness. So as a result, there will be a layer of thickness exceeding TL, of course. So this is the distance from here to here. So it is of course larger than TL, and our objective is to make it TL. This step of elevating is of course required so that during next step, which is sweeping, only the material above the part should get disturbed, means only this much part of the liquid resin should get disturbed, not this one. We don't want to disturb the rest of the material which is available here. So this is called as elevating. Now after elevating, sweeping starts. So here you can see there is a doctor blade which moves from back, which is moving from left to right here in this case. So at this point, the recoating blade travels from one end of the wet to another end and sweeps the excess material from this region. For majority of the part geometry, the optimum sweep period is about 5 seconds. So this operation usually take around 5 seconds. However, it appears that the recoating behavior is quite sensitive to the presence of trapped volume here. For instance, two parts without trapped volume, changing the blade velocity in the range 5 to 120 meter per second does not significantly affect the final layer thickness. However, this is not the case when there are trapped regions or trapped volumes here. In that case, you have to be very careful and go slow so that you do not disturb this particular trapped volume. We elevated this part, right, because we want to exclude this material from the already having material here region. But this trapped volume cannot be excluded from here, and hence if the doctor blade will go with a very high speed, there will be waviness here, and that will cause problem later on. Therefore, if the trap volumes are there, you have to go slow. Now the question comes, what should be the distance between the doctor blade and the part that is represented here by LG? To get the desired layer thickness of the liquid resin, which is TL. And as you can see in the diagram also, the gap between the recoater and the cured part or the top surface of the cured part is greater than the required layer thickness, which is TL. Now, what it should be basically? How large this value should be than the required layer thickness TL? So, for that, let us consider the case where there is a moving plate and there is a fixed plate, and in between there is a liquid resin. We will try to analyze the velocity between the moving and the stationary plate, and we will get an approximate relationship between the gap between the recoater and the top surface of the part and the desired layer thickness. So let us now consider the fourth step of recoating, that is sweeping. So if we ignore the viscous behavior of the resin, we would expect the resulting layer thickness L to be equal to the preset gap G between the blade and the part or previous built layer. But that actually doesn't happen because of the finite value of the surface tension. Due to this finite value of the surface tension, some resin used to adhere to the trailing edge of the blade, and as a result we get a bulge shape at the back side. Also, due to the viscous drag, there will be a bulge close to the leading edge as well. This is the leading edge because it's moving in this direction, the blade is moving in this direction, and this bulge looks something like this. Due to this, the actual layer thickness which is spreaded or deposited on the previous layer is always less than the gap between the blade and the part. Now, as we are going to design the machine, what should be the value of this LG so that I can get the desirable value of TL? So for that, let me consider the velocity distribution under the blade like you are seeing here. Here you can see the resin which is close to the blade is having a velocity equal to the blade, and of course because the resin will adhere to the blade here in this zone, while the resin which is close to the part will not be moving at all and hence will have zero velocity. Hence at this location the resin is not moving at all. While on the other hand, what you are seeing here, the layer will get deposited very far away. If you look at very far away, we can see as a whole that the layer is getting deposited with a rate of VB into TL, the mass flow rate or the deposition rate. So if we follow the law of conservation of mass, we will find that the flow rate in this zone which is very far away and in this zone which is under the blade should be equal. Now how can we find out the flow rate under the blade? For that we can assume that, like I said, the velocity is 0 here, so I am writing 0, and velocity is equals to the blade here, hence I am writing VB here. Assume that this is the 0 distance from the part and this is y distance from the part, and the layer and the velocity is changing linearly from this point to this point onwards. Now anywhere in between, if I consider at a distance of y a small element of thickness dy, assume that it is y plus dy, and of course this is y, then the mass flow rate under this zone will be equals to, the q will be equals to, better write it dq because this is the small strip we are considering, dy into the velocity of the liquid resin in this zone. Also it should be multiplied by the width, of course, and assume that the width of this entire system is unity, that is 1. So this is the mass flow rate. Now if you want to calculate the mass flow rate completely under this zone, you need to integrate it, and we will integrate this function of velocity into dy from 0 to the total gap, that is Lg, and that is what written here. Hence you can get the total flow rate. So the total flow rate will be equals to integration 0 to Lg Vy, the velocity anywhere in between, the resin velocity anywhere in between, into dy. Hence, Vy, which we can easily obtain by writing the equation of line passing through point 0, 0 and Vb, y. Anywhere in between in this line, we can find out the value of Vy. It will be equals to Vb by Lg into y, the linear variation. Now we'll replace the value of Vy with this function in this formula, and finally you will get Q equals to, if you further integrate it, you will get Q equals to VBLG by 2. Now this flow rate which we are getting under the blade should be equal to the deposition rate or the layer spreading rate at very far away location. We will not consider close to the blade because in that case the thickness may be different, but at very far away the thickness will be definitely TL, that is the thickness of the layer spreaded, and it is spreaded when the blade is moving with a velocity of Vb. Then of course the flow rate or the deposition rate will be equals to Vb into the thickness of the deposited layer or the spreaded layer. Now these two flow rates should be equal due to the conservation of mass, and hence the Vb will get cancelled, and finally you will have TL equals to Lg by 2. So whatever the gap between the blade and the part's top surface is, the deposited layer or the spreaded layer thickness will be half of it. So simply, if you want to deposit a layer of 0.01 micron or 0.01 mm assume, then in that case your gap between the blade and the top surface of the part should be 0.02 mm. Now the next is obtaining the build position. So in this case the elevator lowered again such that the part is in the right position for scanning the next layer. The resin surface at the beginning of this stage is still disturbed. You see here this waviness, it is still disturbed. In particular, owing to the finite surface tension effect, there is usually a visible crease even at the solid to liquid interface around the perimeter of the part. Experiments have shown this crease fades away exponentially over the time. So after obtaining the build position, as this crease has to be gone away, we need to wait. And this waiting is called as Z wait, and that is our next step. After obtaining the desired position, we have to just wait at that particular Z height. A waiting period is introduced for the resin surface to blend and reach the configuration as shown in this figure. So this Z wait is basically determined through the compromisation between the surface non-uniformity and the build time. If you really want to build part with a very high build rate, then this Z weight should be less. But in that case, you will compromise on the quality of the part you are producing. One need to choose a longer Z weight when a larger thickness layer is chosen, because if the thickness layer is larger, of course the waviness will be more in that case. So these observations will show you that the Z weight is going to be very large. However, fortunately with current technology, it is possible to complete computation and adjust the resin level per layer within 1 second itself. The problem is still noteworthy because practical parts containing thousands of layers are going to be wait at a particular Z level for at least some amount of time, and hence this time is not really very desirable for the good productivity. So this was about the recoating system of 3D systems SLA. But if you recall, in the second type of machine where the instead of deep dipping, top feeding was there for depositing the new layer of the liquid resin on top of the part for the 3D systems SLA, the technology was called as Zephyr. So this Zephyr system has basically a vacuum blade that picks up the resin from the side of the wet and applies a thin layer of resin as it sweeps across the part. This entire process speeds up the build process by reducing the time required between the layer and greatly reduces the problem involved when building part with trapped volumes. So basically this is how it may look like. This is your build platform, and on the one side of it there is a reservoir. For example, this is your reservoir where we have the liquid resin. Now on top of it there will be a blade which will be something like this, and there will be a vacuum applied to the same. Due to the vacuum applied here, it will take some material from the reservoir, and as this will fill with the desired liquid material here. Now this reservoir will move from this end to this end of the liquid wet, and while moving from this end to this end, the liquid material will fall. It will look like a curtain and it will spread it over the liquid photopolymer bed. Here you can see there is no issues related to the trapped volume. Whatever the trapped volume is there inside the part which we are building, it is definitely independent of the recoating system. However, we have to make a compromisation on the quality of the layer which we spread by this technology. Of course, by the deep dipping process, the spreaded layer is more accurate. So we have discussed today about the recoating system also. Now let us just quickly look at some of the options for the Z-axis of the machine, that is the last subsystem. So usually in the SLA system, lead screw or ball screw are used for the Z-axis. Also in some systems, rack and pinions are used, and sometimes also parallel kinematics such as scissor lifts are used. So scissor lifts look something like this. So this is the build platform, and now if this end will move, of course this will lift up. So benefit of such parallel kinematics is a very small foot area. Here you can put even parallel scissors like this, right? You can put parallel scissors, and hence you can achieve a very large build volume in the build direction by having a very less amount of area acquired on the y direction. So such kind of mechanisms are usually used for Z-axis in the SLA based processes. So with this we have completed the discussion on the 3D systems SLA, and we have discussed in detail each and every subsystem available in the machine. These subsystems were the laser beam, the curing of the photopolymer. Also we have discussed the galvanometer and the optics involved for deflecting the laser beam from a particular point to another point, and also we have discussed about the recoating system, which is the most complicated system in the 3D systems SLA as compared to the other subsystems. Also the Z-axis is basically they utilizes lead screw or rack and pinion, or then can use the parallel kinematics. So these are the subsystems for 3D systems SLA. Thank you very much.